speak about geometrization. On the local elements. This is about the conjecture I did something like 2 years ago. But before speaking about my conjecture, I will recall you some classical cases of geometrization in the context of the geometric Lagrange program. Some kind of introduction today about this kind of stuff, geometrization. Let me recall you, tell you some things about it, about this type of thing. This is a classical case. To say typically that you will find the work of Ringfeld, Lemont, and what like that. Thus, the idea of geometrization is the following: to upgrade a function to a shift, and even to a perverse shift. To say, you have a statement about function, and you upgrade it to a statement about perverse shift via Grothendieck's dictionary. Between the shield and function. Let me recall you quickly what is this dictionary. Let's say X is an algebraic variety over the finite field FQ. And the dictionary goes from shields to functions. So let's say you have F like that. This is, more generally than a shift, this is a complex of shields bounded with constructible cohomology on X. This is an étal complex of étal shields with QL bar coefficients. And to such an F, you can associate the following function on the finite set of FQ points of your algebraic variety. This is the function in value of QL bar. Of course, as usual, I identify from P and so on. Just to point X, you associate the trace of Frobenius X of the stroke of your shift acting. Frobenius acting on the stroke of your shift. X star F, X bars here, is the geometric point over X. Okay, but you start with a shift, or more generally complex of shift, for the étal topology, and you associate to this complex of shift the trace of Frobenius function on the FQ point of your algebraic variety. This defines you on this, the object of this category. An object is only Dirac category. You associate a function on the FQ points X is valued to QL bar. This is this correspondence over A. And in fact, I told you, you apply the function to a perverse shift. This may seem a little bit weird, but why do we want to have perversity in this context? And this is for the following reason. But in fact, information here associated to a complex of sheaves depend only on the class of this complex of sheaves in the atomic group K0 of this triangulated category. ABC. Well, it's an exercise, it's immediate that this K0 is the same as the atomic group of the abelian category of constructible Q bar sheaves on X. X égale, non plus. Since you set the atomic group of this abelian category of constructible sheaves, the same as the K0 of this triangulated category. This is abelian, but this is not Artinian. Okay, a lot of finite length here. But changing the T structure on this barely derived category, you can write it as K0 on the category of perverse sheaves on X. Q bar coefficients. Okay? Just okay, between the change of T structure, the K0 does not depend on the R of the T structure. And this one is abelian and Artinian. Any object, any perverse sheaf has finite length. Okay? So this is K0, is a free abelian group on simple, or you may want to call them irreducible if you want, simple perverse sheaf. Thus, you can see this correspondence, the correspondence that associates to a linear combination, virtual linear combination of simple abelian perverse sheaf, a simple perverse sheaf X. You associate a function to this linear combination, and now we have the following Chebotarev density theorem. It tells you the following. F is a simple perverse sheaf X. It is completely determined by its trace of Frobenius function. Well, not on FQ points. On all FQ to the n points for all n greater than or equal to. So you have the trace of Frob. Sorry, but yeah. I trace of Frob to the n points. Okay. Thus, you don't lose information if you like that, if you restrict yourself to the level of perverse sheaf instead of complex of sheaf or instead of constructible sheaf. This is why we go looking for a perverse sheaf. But technically, we can use the two most basic examples of this geometrization, and then I will go to much more complicated example after that. Let's say psi is a character with analytic values, with coefficient Q bar of the additive group of finite figure Q. And to this, you can geometrize it to the Artin-Schreier sheaf over the alpha line. Okay. Let's say chi the character character for the unit of this finite field with values in QL bar, start, then you can geometrize it to a Kummer sheaf, c'est kappa chi like that, is a Kummer sheaf on GL. So just two basic examples of geometrization procedure. So character is associated with perversion. There are much more complicated examples, of course. This is typically, for example, Lustig character sheaf theory. You have even much more complicated examples. I mean, geometrization. You can geometrize local orbital integral via fine interfibers. Stuff like that, or family of orbital integrals via, let's say, via H fibration, like in the work of Ango, and so on and so on. You have plenty of examples of geometrization of this kind. This is not always exactly this procedure, but this is some variant of it. Okay. And geometrization is really a powerful procedure. It's a powerful tool because we have some new operations at the level of sheaves. Typically, let's say you have U, an open subset of the algebraic variable X. Let's say you have a function f on the few points of this open subset with values in QL bar. Let's say you have geometrized it, and you are able to geometrize it. Geometrize. This is to say, this is the trace of Frobenius function of a perverse sheaf f on U. Then you have a new operation at the level of perverse sheaf. Typically, you can look at the intermediate extension of this perverse sheaf. That is a perverse sheaf on X. And thus, like that, you have a new function on X of Q via this procedure. I mean, there is no, you cannot describe this procedure at the level of points like that via an operation of functions. You have a well-defined operation of sheaves that does not exist at the level of functions. That is this intermediate extension. And what else? You have plenty of rigidity project properties, I mean, something great, just to motivate properties of perverse sheaves that do not exist at the level of functions. Typically, for example, you have the decomposition theorem. This is the type of theorem that is used by Ango to prove this fundamental law. Once you have you can apply the function to a perverse sheaf. You have plenty of new rigidity properties for sheaves. very vague up to now. But now, I'm going to be more precise and talk about bundles and non-program. Yes. Let me introduce the geometrization of the global Riemann correspondence of function field for function field. This is work of Greenfeld, Lemont, and Kelly Torre-Viola. Some work that was a big inspiration for this question we'll speak about later. This is why I want to speak a little bit about it. But let's say that the setting is the following. Let's say X over the finite field FQ is a proper smooth algebraic curve. For example, the positive line if you want. You won't have a lot of depends what you want to do. And let's say K is the field of rational functions on this curve. Well, moreover, you have to suppose that X is geometrically connected as usual. And then you have the following theorem of the Greenfeld. Before stating the geometrization of this global Lagrange correspondence, let me recall the classical global Lagrange correspondence in this case. In a particular case, but it's everywhere around that case. But let's say rho is a Galois representation is analytic coefficient equation n of the Galois group of this global field K, that is the function field of your algebraic curve. And you suppose that this Galois representation is irreducible and everywhere unramified. It's unramified at all finite places of this global function field K. Okay. Then Greenfeld was the GL2 case, that forms the GLN case. They exit the function f, it will be an automorphic function. So this is a function on GLN of the LN of K. It is automorphic. It's the invariant on the left by GLN of K. It is, moreover, everywhere unramified. Invariant under the following maximal complex group, because here the V's here are the finite places, the curve X, to say the closed point of this curve X. And KV is the completion of the global field K isoplane V. O of this is the ring of integers. Here this is the addend of its global function field. This is a function with values of Q and R. It's non-zero. That is moreover customary. such as for all finite places V of the global function field K, F is an eigenvector of the unramified equivocal operator at V with eigenvalues what? Which eigenvalue? The eigenvalues of the action of these equi-operators are given by the matrix of Frobenius at V. For V is an element conjugates a class of elements that might this global zero group. Okay. Given by a rho for V, this is well defined, the rho is everywhere unramified. Thus, this is given by not only this, not this matrix, but by the eigenvalues of this matrix, via the unramified local magnet corresponding. Okay, this is a global statement, classical statement for the global magnet correspondence of function fields in the everywhere unramified fields. And now, what does it mean to geometrize this statement? This means the following. Thus, we have different objects to geometrize. Let's look at the statement of this theory. First, I'm beginning with rho. Trivial to geometrize rho. I mean, to give yourself rho is the same as to give yourself E curve. This is a QL bar rank n QL bar local system. X irreducible. When in fact, I've been wrong here, I mean, I should have thought geometrically irreducible. To say, after extension of the scalars from F2 to F2 bar. Okay. Thus, rho is the same as a rank NQ bar curve. Okay, because I suppose that rho is everywhere unramified. This is the same. Then, what is the geometrization for this function here? Just to geometrize the function, I told you before, you replace the function by a pair sheaf. On what? As for this, you need to geometrize these double classes here. Thus, you need to geometrize this double classes. And the geometrization of this set is done. This is a stack of rank n vector bundles on the curve X. Thus, Morningside V FQ, but given S, this is a group of rank n vector bundles on the family of curves, the trivial family of curves associated with X. When you do X times S. This is a group weight of this vector bundle of X. This is a classical statement due to Weil. It goes back to the 50s. Okay, because in fact you have bundle of FQ as a group of it. This is the following quotient group of it. Just look at the group inversion of this double quotient. Now, to geometrize the automorphic function f in the preceding statement makes sense. We want to upgrade the automorphic function to a pair sheet on the stack of rank n vector bundles. But there is a last thing we have to geometrize in the preceding statement, because we said that our automorphic function is an eigenvector for the action of some equal operators. We have to geometrize those equal operators. We have to geometrize those unramified equal operators. And the geometrization of those unramified equal operators is what we call the equal correspondences. So this is a correspondence between the stack bun and itself, or itself times the curve, you see. Just to define them, those equal correspondences, we need to fix the co-height in the positive chamber. Here, T is the standard torus of GLN, maximal torus of GLN. It's just diagonal matrices, just the plus. This is the usual Z to the n plus, the direct increase, decreasing sequences of integers. And then the geometrization of the equal operator associated to the double class of mu in the equal algebra, given by the following. We have this equal stack. This is a correspondence, I said, between two things. On the left, there is our stack of vector bundles. This is map on the left. The second map is denoted like that. And it goes to our 1 times the curve X. Thus, what is this moduli space? Equal mu, like that. Because I really want to speak about it because in a few minutes I will give this perpetual stuff and good theoretical basis. Just to have this in mind. we try to mimic this in the perspective world. Thus, even if you know this by heart, we need to recall it. Thus, if S is a scheme white, S is a scheme over FQ. Okay. This stack equal U associated to S, the groupoid of triples like that, E1, E2, S, U, that. Thus, what is E1? You get it here. As I told you, E que sits over 1 and 1 times X. Okay? Thus, E1 is a vector bundle on X S. Okay? And E2 is another vector bundle on X S. Okay. S is a section, small s is a section of the curve X, which means that small s is a section over ds of the curve X, which is the same, as to gives you a section of X times S over S. And this, you can see it as a degree 1 relative Cartier divisor on the family of curve XS over S, parametric. Thus, we have a vector bundle E2, like that, a vector bundle E1, a degree 1 relative Cartier divisor on the family of curve S, and the last element is the U. This is a modification of vector bundle. This U is a modification between E1 and E2, and it is a modification that is supported on this Cartier divisor, and we denote it D, it's a D. D is Cartier divisor. It is supported on D, that's to say, this is an isomorphism between E1 and E2 outside this Cartier divisor. And then there is this condition bounded by mu. Okay. This means that this condition here, what does it mean? This condition is the definition of the Hegel stack, that we ask that the relative position, fiber-wise, be more precise, fiber-wise over S. Fiber-wise over S, you have a modification of two vector bundles on a curve over phi. The relative position, I'm being vague here. Yes, most of you know what it means. Given each time you have a modification like that, and you look at yourself as a divisor D, you have two lattices inside the same vector space. And those two lattices have a relative position given by the modification U is lower than or equal to mu. I mean, to any two lattices like that, you have a relative position that is associated to these two lattices. And it is an element of a positive vine chamber, and there is an order on this positive vine chamber. We ask that. Lower than or equal to mu. Another way to define it, this is a condition on Hodge polygon of the modification. Okay. And I'm speaking about Hodge polygon, I mean, because to any modification like that, you have a kind of set of Hodge polygon. And in a few hours, I mean, there will be Hodge polygons, but in the context of periodical theory. And you can really interpret them. I mean, like in Fontaine, the definition of fit on the FIMO2, you have Hodge polygon. You can reinterpret those Fontaine's Hodge polygon in terms of this Negus stack. There is a dictionary between geometric language and classical language of periodical theory, and so on and so on. That's okay. I'm being vague here. I will be more precise in the context of my conjecture. I'm just recalling basic things. And now the geometrization theorem is due to the Greenfeld for GL2. Lomont, vous constructed what we call the Lomont sheet, part of the proof of this conjecture, of this theorem. And Frankel, Gascory, Villeneuve, is that you start with your local system on the complex. So you have the geometrically reducible local system on X. Then there exists F, some irreducible perverse shift on Bun. This perverse shift is the geometrization of our cuspidal automorphic function. That is cuspidal. I mean, there is a geometrization of the notion of cuspidality, because you can define what we call, some constant term functors for complex of sheaves on Bun, easily defined. On Bun cuspidal, that is an Ecke eigenshift with eigenvalue given by this local system. E curve we start with. I tell you that E curve is the one that is linked to this Galois representation of E curve is local system of X. Okay. I will make this more precise. Okay, so you start with E curve, and then there is an irreducible perverse shift, cuspidal, that is an Ecke eigenvector, eigenshift, with respect to those coordinates. It means eigenvalue given by E curve, and via what? There was in the preceding statement, there was a sentence, a part of the sentence saying via the Satake correspondence, isomorphism, via the unramified local Lagrange correspondence, I said, and here this is via the geometric Satake correspondence. Via the geometric Satake correspondence. That's what is the geometric Satake correspondence. This is the geometrization of this ramified local Lagrange correspondence. That's what does it mean? Last statement. This means the following. If I pick some co-wide mu, it is minuscule. I begin with this case because it's simpler to state. Then I apply my correspondence, geometric equicorrespondence to my perverse shift F on 1. I pull it back. Here's the left map of the correspondence. I push it forward. Here's the right map. Okay, there is some twist here. There is a shift first of this complex, and there is a tape twist, or half tape twist, it depends. Here, O is not the Galois representation of before, but this is the half sum of the positive group, as usual. Okay. Let's forget this. And this is a homomorphic. I told you that F is an eigenvector. If I apply this correspondence to F, I obtain F times the eigenvalue, and the eigenvalue given by R mu lower star E. That's what is this based. That's R mu is a representation of the algebraic group GL seen as an algebraic group of log QL bar. This is the Lagrange dual of GL. Here is GL itself. And this is very concrete. I mean, this is nothing else than the exterior power of E, I times if, let's say mu typically is 1, 1, 0, 0. Here this is I. And this is a new local system that is built out of equal. I will tell you what it means when mu is non-minuscule, but let me tell you that here the Satake isomorphism between the equialgebra of GLN, let's say at a place V, the GLN of KV modulo GLN maximal for KV. You have an unharmonified equialgebra and you have a Satake isomorphism that identifies you with the Grothendieck group K0 of the algebraic linear representation of GL over QL. This is Satake classical Satake isomorphism. And if mu is minuscule, Satake transform of the double class given by mu in this Grothendieck group is the class of this algebraic representation R mu. That is, this is not an omega, this is an R. This is, I mean, I can tell, but this notation R mu is standard for the algebraic representation of the Lagrange dual with highest white mu at. I mean, any co-white like mu of the algebraic group G, that is GLN here, defines the white of the Lagrange dual G. Okay? Thus, you have highest white as a representation R mu. And when mu is minuscule, you have an explicit formula for the Satake transform of the double class of the given value. This is this algebraic representation RU. This is why this RU shows up here. Okay. When mu is non-minuscule, the explicit description of the Satake transform of the double class given value is much more complicated, and it involves Cauchy-Lustig polynomials for the final variable. I need to record this because in my context I will have the same type of things. So I need to record this. This is classical. That's for any mu, not necessarily minuscule. As you apply the equal transform F, but the shift here will be much more complicated. It will involve the geometrization of this Cauchy-Lustig polynomials. And because the geometrization of those Cauchy-Lustig polynomials is exactly this geometric Satake, given that this geometric Satake correspondence on the final exponent. Yes, let me write it ICU like that. I will tell you what it is later. This is isomorphic to F. And again, write that F is an eigenvector with a eigenvalue the same RU. RU star equal. RU here. I write it white representation of G hat. It is GLN in this case. GLN is GLN with IS right. Mu hat. Okay. And this list I told you here. This is geometrization of some Cauchy-Lustig polynomial. Show up in the description of this Satake transform of the double class of mu of phi. Conclude this. You find the type of objects, combinatorial objects, and how do you define this IC mu? In fact, you realize that this right, I will think about this later in my context too, this right magnetic morphism that defines this echo correspondence is locally trivial. Étant locally trivial phi duration. In what? In GR lower than or equal to mu. This is an object sits over X. This is a scheme over X, the curve X. And this is a this is a closed sugar cell. In the Beijing Ringfeld to find mass planet. And this a Benito-Fine-Grassmannian. This is the relative version of the curve of this classical Fine-Grassmannian. This is the twisted version for the smooth.
Sorry,
yes.
the tensor product, F tensor IC mu,
yes.
relative with, is it on?
Sorry. Wait, 2 seconds. IC mu leads over echo mu.
Ah.
Let me withdraw something. Representation. You have this equilibrium. You have something on the left, we don't care, and we have something on the right. You have 1 times x.
So that is H right arrow or
yes. I put on the right, H right.
On top, the formula.
Oops. Thank you. The Russian notation is too difficult for me. Okay? And thus IC mu is an equilibrium. Lead on this. Okay. And this, what did I say? Yes. And using this vibration property, you can transfer. I'm being vague here, but it's not difficult to do. The intersection cohomology complex IC mu on this closed sugar cell to something still not IC mu on echo mu. So you have a closed sugar cell. The open sugar cell is, is either of Fine-Grassmannian, one. And in terms of the relative version, it's more or less the same as the classical version. Don't care about this for the moment. This closed sugar cell is a compactification of this open sugar cell that is smooth. The open sugar cell is smooth, and this one is singular in general. Thus you have an intersection cohomology complex of this closed sugar cell, and using this locality property, vibration property, you can transfer it to a Kerner sheet on this echo stack. I will be more precise later in my text mail.
So it should be the pullback of F tensor with IC.
The pullback of
F and the other.
Oops. Thank you. Don't forget anything. When mu is minuscule, I think I wrote it well. Okay, fine with it? Okay. And that's just another remark. Is that this closed sugar cell is nothing else than a classical flag manifold. G not P mu is a parabolic mu if mu is minus 1. Okay? Which explains the fact that when mu is minuscule, the formula simplifies a lot because in this case, this closed sugar cell is smooth. Its intersection cohomology complex is nothing else than a Q and R shifted and twisted so that it has white zero. Okay. Okay. As you see, well, it took some time, but I really wanted to record this before I go to perfectoid complicated stuff. Okay. just some introduction. Now, I will switch to the context of the curve I studied and defined in my work with Fontaine, in terms of p-adic theory. You will see the geometrization statement, this conjecture is a little bit more, a little bit different. We are going to try to adapt the statement. At some point it's different. Just I will speak about this curve. First, we can do some things about this curve I studied with Fontaine. Just two notations, I mean 2 or 3 notations that we use everywhere during the talk. E will be a p-adic field, I mean a local field. But not necessarily p-adic because maybe it can be the equal characteristic case local field. You will see that in this case, the equal characteristic case, everything is much more simple. Or it can be finite degree extension of the p-adic number. Everywhere, E will be this. FQ will always be so as you field. And at some point, I will need to fix some information so it's not necessarily. And I will denote it pi. Moreover, I will fix FQ bar, natural FQ bar FQ, and E grid are proportion notation for the completion of the maximal unramified extension of E associated to this choice of FQ bar, and sigma. This will be its frobenius of this maximal unramified extension. Okay? And now, I will use this coupling set, B of G. Oh, sorry, I forgot G. What is G? The G is a relative group of now this local field T. And very quickly, I mean, in my conjecture, it will be quasi-split, but for the moment, I don't need it. And I can use, we have this coupling set, B of G, that shows up in a lot of work. I mean, typically, the computation by Conveys, I mean, of the asymptotic data function of PL type Shimura variety. B of G is a set of twisted sigma conjugacy classes inside G of equilibrium. This is twisted conjugacy. This is convex. And now, if I do a comparison between what I considered before and what I will do next, before I was geometrizing this set of double classes, GLN of ZLN on the right, GLN of maximal compact, and okay, and now I will geometrize this set of BG. So we explain you today how to geometrize B of G. Thus, I will geometrize B of G. More precisely, I will write the objective is to write B of G is a point of bun G. And bun, let's say bun over F2 bar. Forget the G notation. It will be fixed everywhere. And this will be a perfect stack. perfectly stacked. I mean, this is some kind of the analog of algebraic stack. That's perfect. Okay. Thus, how do you construct this curve? Thus, you start with S. This is a perfect weight space. Over FQ. Not FQ bar for the moment. Also very quickly as quickly as bar. And to this, there are two steps in the construction of this curve. The first step is to construct a space I denote Y sub S. This is a VAD space. And it is equipped with an action of a Frobenius phi. There are two cases. I mean, with respect to those two cases, the first case, when E is equal characteristic, is much more simple. So we begin with this case. There is a unified way in both cases simultaneously, but this first case is much more simple. Thus, if E lower oversized field, over finite field FQ, then Ys, by definition, you can take it as a definition, this is a puncture disk, an open puncture disk over S, it's a Gaussian space, magnetic space, of the variable pi, inside the affine line over S. Thus you remove the origin, this is punctured, and you take an open disk, this absolute value is thinking of pi second. Pi is the coordinate. Of course, in fact, you can write this, I mean, the categorical product in the category of analytic addict spaces as star S times star FQ double bound. This is not an exercise. This trivial fibration in open puncture disk over S is a categorical product, in fact, in the category of analytic addict spaces. And you have two structural maps. The first one is, I told you, this is a trivial fibration in open puncture disk over S. So you have a classic standard structural map over S. Here, like that. But this one is locally of finite type, topological finite type. This is a standard structural map that shows up in the K-rigidity geometry. But this is not the one we are interested in. We are interested in another structural map. I mean, S is over FQ. Okay? There's isomorphism from the open puncture disk over S towards the open puncture disk over FQ. I mean, you can really consider FQ as a dynamic space. I mean, FQ is equipped with the discrete topology. And since the variable is pi here in this open puncture disk, this is nothing else than the addict spectrum of E. And this structural morphism is not topologically, not locally topologically finite. And this this is really the structural morphism we are looking for. Forget this one. I mean, maybe you are used to this one, but forget it, this one is. Because I told you, Y is an ELE space. It's an ELE space. And here you see the ELE space structure. And what is the action of the Frobenius of this open structure disk? Phi. Here. Just this product formula. This is the Frobenius of S times the identity. Be careful, this is not the identity times the Frobenius of E. If you do this, you will obtain another space I will speak about later. And you see, this structural morphism is not Frobenius invariant, because the Frobenius mark is a non-trivial S, but this one is Frobenius invariant. The action of Frobenius here is an action of an automorphism by automorphism of ELE spaces. This is the main remark in this context. So this case is quite easy. I mean, one characteristic.
Before you release it, what's the notation of this notation? You mean the connected component?
No, the points.
The points.
I will define it later. I mean, in this case, I mean, grosso modo, I mean, you take the same definition as let's say Le Monde or Bailey's book. I mean, for an algebraic stack, you have the definition of the points of the stack. So you take you evaluate the stack of all possible fields and question by some evident equivalence relation. Or we use the precise definition. This is a little bit ad hoc, but it works. To any algebraic stack, I mean, in the classical context, you can associate a topological space of points. Okay. So let me give you some hints how to define those things when E is a finite degree extension of the theoretic numbers. How can you guess what you have to do? Just look at the following. You want to define the space Y when E is QP. And if you look a little bit here, holomorphic functions on this open functor disk are power series of the variable pi. And power series of the variable P, holomorphic functions of the variable P are given by field vectors. Let's say S here is a phenoid perfectoid. Later, I'll tell you why you don't need to care about R plus. Framed by R plus. And now, we look at this Fontaine ring A1. I mean, I will note it like A double bar like that. So this is the ramified bit vectors of R0. And those are power series like that. Okay. Since R is perfectoid, R0 is a perfect thing. I told you that R0 is a set of power bonded elements in R. I mean, R0 is a set of elements in R. If you want that, the number of x is lower than or equal to 1, where this norm exists by hypothesis, I mean, on any perfectoid algebra, is a power multiplicative norm of planar algebra that defines the topology of this perfectoid algebra. This is the perfect ring, and thus when you evaluate, when you take the field vectors of this, I mean, if you're not used to, I mean, the ramified vectors are the same as the field vectors when E equals Q. Since R0 is perfect, the field vectors have a unique power series expansion. And you really have to think about this as being an holomorphic function of my pi. And you define what? Okay. You can define A plus in this context. Plus A plus is a set of holomorphic functions in A1 such that F mod pi is defined to R plus. This is to say the choice of an R plus defined on A plus. Okay, if you want to write it in another way, this is the diagonal of elements plus pi times A. Okay? We want to define the space Y. Okay, and then, by definition, say Y sub S, this is the spectrum of this A thing. And you remove the following plus subset of pi or Schiller of pi R vanish. Here, pi R is what we call pseudo uniformizing element. Pseudo uniformizing element. This is the topological identity that exists by definition of a perfect ring. This formula seems complicated. I'm going to explain you in a more concrete way what it means. Let me tell you that the Frobenius that acts on this space Y is given by the following formula at the level of functions. This is the usual Frobenius of the Lie vectors. To say you raise Schillers to the Q power, and the variable pi is unchanged. Okay. Okay. So what does it mean concretely? I should be more concrete. Because this formula, I mean, is not. Well, if you are an expert, I mean, you know, you see what it means. Maybe you will not visualize what it means here. Plus, concretely, in fact, the space Y, by construction, in this case, in the case when S is a figurative perfectoid like that, is Stein. In particular, it is completely determined by the Fréchet algebra of holomorphic functions on it. And I can give you a formula for this Fréchet algebra that is quite complete. Also, half complete, because there is a completion projector. This Fréchet algebra is a completion following E algebra. So you take your Fontaine ring A1 and you localize it in the following way. That you invert pi, and you invert this Schiller of this pseudo-uniformizing. That. And those are the set of power series. Like that. I inverted pi, those are meromorphic functions at pi equals 0. And there is a condition that the sequence satisfying this Cauchy-Euler expansion is bounded on bar. Okay, here the element x and are in R now. Before they were in R not, now inverted this Cauchy-Euler. Okay, this is the completion of this ring, which is quite concrete. With respect to the following Gauss norm. This is the family of Gauss norms parameterized by some radius, rho, that goes strictly between 0 and 1. You see, these radius reproduce something linked to this open punctured disk. And the norm of such an expression on top of the radius rho is given by the usual formula that you know. An adaptation of the usual formula of the Gauss norm. Supplément of the n coefficient times rho. Here, the norm you use on R is you fix a norm. This is an algebra R that is power multiplication. And that defines the topology of R. This exists by hypothesis. Okay, but this is more concrete than before, but still, I mean, the element of this completion can be very concrete. Okay. I gave you the formula for the space Y when n is affine perfectory. Then you can do the construction R plus is space Y associated to the spectrum of R plus to a functor from perfectly spaces of F2 to R E and E spaces. I did the affine perfectly case, but I told you this construction has a good localization properties with respect to rational open subsets, rational domains. And moreover, we have the following formula: Y(S) diamonds. Okay, here, either you do diamonds are relevant. And this is S. But up to your lucky, I mean, if you don't, you have to forget this formula if you don't. At some point, I mean, you cannot escape. This is S right here. This is a nice formula that is, you see, this is some analog of the formula I gave for the open puncture disk. I told you the open puncture disk is a categorical product of S times X bar E. And you have this analogous formula in the unequal characteristic case. Okay. And the Frobenius here is valid, the Frobenius phi is valid given by form S times n with respect to this formula. Okay. And now, I told you I want to define a curve. Parametra is defined by the category space S. This is not really a curve, this is a family of curves parameterized by S. I told you there are two steps. First, there is this construction of the space Y. This is some kind of Stein space. Fiber of S. Now, just for S, category space over F2. Set XS. This is space Y for the local powers of this problem. And this makes sense as a D space. because if you take the picture of this open function of this, well, picture given by those cows now, you can define some analyte inside this space Y, and phi is homogeneous, and this is an isomorphism between the annulus with radius with radii inside the interval ρ1, ρ2. Here ρ1, ρ2 are strictly between 0 and 1. There are some two radius inside this associated with this open structure disk. If you apply Frobenius to this annulus, you obtain an annulus with radius. I don't know how to say it. ρ1 over 1q, ρ2 over. As you see, Frobenius is a dilatation of this open factor disk. It sends everything to the boundary of this open factor disk. And because the radius is strictly between 0 and 1, you see that the Frobenius acts in a properly discontinuous way without fixed point on this fixed point. So this quotient makes sense as an ELE effect. Formula here implies that phi z acts properly discontinuously without fixed point on the space Y, and this quotient as a main. Okay. Thus, really, XF is really in some sense family of curves X associated to each residue field of S. You really have to think about it as really being this family of compact ELE Riemann surface. For example, compact ELE Riemann surface. Okay. Of course, this does not make a sense because there is no morphism from S to S. Because the question by Frobenius, so remember, there are two structural morphisms. This are S. One goes to S, the other goes to spa Q the record is spa E. And this one, you can, if you divide by Frobenius, here you cannot divide. And this is really the family of curves. I mean, and those are really the object, the typical object custodius contain. I mean, in another way, there is an algebraic curve of which I talk about. Okay. And let me tell you a little thing before finishing about vector bundles. I introduce this stack of, I want to introduce this stack of vector bundles on this curve. So I can use an hybrid maximal quantified extension of E together with Frobenius sigma. Okay. And I will look at few modules those are coupled C5. This is typically the object that shows up in this Dionne-Malin classification theorem. Typically, this is the crystalline homology of the proportions are divided by IT over 3, with P inverted. Here D is a finite dimensional hybrid vector space. Okay. And phi is a sigma linear automorphism. Suppose now that the space, perfectly space I used before, S over Fq is in fact defined over Fq bar. Then this implies that the space Y is in fact defined not only over E, but in fact over E grid. Okay? And the action of the Frobenius here, used to define the curve XS, quotient, is given via this morphism by the action of this Frobenius sigma on this maximal rank. Okay. And I tell you, there is a front law from isocrystals to our vector bundle on XS. Just to have the crystal D5. You associate the vector bundle E5. How do you do this construction of this vector? How do you associate the vector bundle to an isocrystal? This is quite simple, in fact. Thus, you start with a vector bundle over Y, that is a trivial vector bundle, with fiber D, which is possible because Y, is defined over the grid, and D is a Lie vector space. So you can define this product. This is a trivial vector bundle over Y with fiber D, and you take now a twisted product with respect to Frobenius. So there is an S here, S. And this is the geometric realization of this vector bundle. As you see, this is a vector bundle that is trivial when you pull it back to the cover Y of X. This is after this uniformization of X, you put it back, it becomes a trivial vector bundle with fiber D. And the descent of this vector bundle to X, that is to say the automorphic factor, is given by the Frobenius phi. Thus, later I will use the following notations, maybe, probably. If D, for example, if D is an integer, I can define a Lie bundle O of D. That's by definition. The vector bundle associated to the following rank 1 isocrystal, E curve, and the Frobenius is divided by pi minus D times C. And this is a Lie bundle. I will give you a state theorem. I will stop this here after today. Let me take you the first main theorem. Let's say S is a geometric point. is to say the LA spectrum, an algebraically closed perfectly free, which means an algebraically closed characteristic P complete value field. Then this functor is essentially solid. To say any vector bundle on X over geometric point is of the form the vector bundle associated to an isochristals. Maybe you can be more concrete. I can give a concrete translation of this statement via Giuseppe theorem. I mean, Giuseppe gives you a description in terms of slopes of this category of isocrystals. I mean, it tells you that this category, this abelian category of isocrystals, is abelian semi-simple, and there is a slope decomposition, and for each slope there is a really simple object, isoclinic of stock lambda, it's completely explicit and so on. And if you apply this completely explicit description, you find the following. If I pick vector bundle on curve X, not geometric point S, then it is isomorphic to the direction of vector bundle O of lambda I. So lambda I are some slopes that are rational numbers. O of lambda I is some stable vector bundle of slope lambda I. Stable means this is the Ardana-Racine sense. Okay, I'll tell you there is a good way to do some Ardana-Racine theory for vector bundle on this curve. It's not evident. Maybe I will play with this later tomorrow to explain you why there is a good notion of Ardana-Racine integration on the vector bundle. It's not evident because a priori we are working with some. What I call a vector bundle in this context is a locally free sheaf of all modules on this radix space. How do we define the degree of this? It's not clear. I will tell you this later a little bit. And you see, this theorem is some kind of generalization, but it's much more difficult to prove than the generalization of Grothendieck's theorem. Description of vector bundle on positive line. And okay, I will stop here.
So any questions? When you say the Semiconductor theorem, you explain it for the simple permission. So what's going on with the constructor sheet? When you say the Semiconductor theorem, you regard the sheet of the simple permission.
Yes.
What's going on with the general constructor? No, with the general constructor sheet. Even the general constructor sheet.
No, but you see, if you take a constructible sheet, any constructible sheet, not perverse.
Yeah.
Take a constructible sheet, F. I mean, you can define its class F is the K0 of blah 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 as before, and you can express it as a linear combination of simple direct sheets. Okay? They have the same place of probability function. Can happen. I don't have any example, but I can do for tomorrow maybe.
Okay.
two constructive machines that have the same types of Frobenius function but are not isomorphic.
Okay.
May happen, kind of thing. Exercise for two points. It's not evident. Okay. Good question.
The second question, maybe then we will formulate it. If I understand correctly, you want to geometrize the Vitogram or something like that?
Vitogram, yes, you can geometrize Vitogram, yeah.
How can I understand this thing we kind of construction in terms of Vitogram?
Vitogram, I will explain this probably tomorrow. Okay. I need some water, some notation, but it will be clear.